I've laid out 5-meter sticks here on my driveway, and I have a remote controlled toy car over here. What I'm going to do is I'm going to use this to collect a little bit of information. Ready? Here we go. In 3, 2, 1. Now I'm going to try the same experiment. The only difference is, now instead of using the remote controlled car, I'm going to use this dynamics cart. This doesn't have a motor in it, and we'll see how that changes things. In 3, 2, 1. We can easily see, just by watching the two videos, that the motion of the two different types of cars is very different. So today, we want to find a way to quantize that. We want to find a way where we can actually see this. Today, we're going to talk about graphing motion. Well, aloha everyone. Today, we're going to talk about graphing motion. And so, when we talk about graphing motion, we mean making graphs of how an object is moving. Maybe where it is, or how fast it's going, or even how much it's accelerating. So, in the beginning of this video, you saw me make a video of the car rolling down or driving down my driveway. And so here's what I did. I took that video and I spent a little bit of time watching it frame by frame, and I did my best to try and figure out when each of those objects was going to pass the 1 meter, 2 meter, 3 meter, 4 meter, and 5 meter marks. And I made a table of that. And it looks sort of like this. That's probably a little bit small. Let's make it a little bit bigger. So that one's for the blue car. And then I did the same thing for the red car, the one that was rolling down without driving. So the blue car was the one that had the radio control, and the red car is the one that was just rolling down without any power. So it turns out, here are the times, and here are the distances for each of them, the blue car and the red car. Then what I did is I made a graph. And I made that graph for both of them. All I did was plot them on the same piece of, or on the same graph here. And the graph ends up looking sort of like this. Let's make that a little bit bigger. All right, so here is our graph. And this graph indicates a couple things. First of all, I'd like to point out a few things. The blue car reached the bottom of the ramp, or the bottom of the driveway, before the red car did. It was a lot faster. It went down the driveway quite a bit faster. By the end, the red car was moving probably about the same speed, but the red car was a lot slower to take off. So because of that, you can see a couple things. The blue car here is going to reach the bottom of the 5 meters before the red car does. In fact, quite a lot of time before. Time is down here on this axis. And you can see it takes a lot less time for the blue car to reach the bottom of the ramp. But they went the same distance. So the same distance in less time means the blue car, on average, was traveling faster. Looking at this graph, there's actually something interesting you can see. You see we have time down here on this axis. We have distance on our y-axis right there. And there's a formula that you learned in your math class. It's about slope. And you might remember that the slope formula, m, maybe they called it rise over run. Or maybe you heard it as change in y over change in x, delta y over delta x. Or maybe you heard of it as y2 minus y1 over x2 minus x1. Well, in this case, our slope is going to be the change in distance, delta d maybe, over the change in time, delta t. And if I remember correctly, a distance over a time was what we called average speed or average velocity, if we're talking about displacement or position there. So what this means is if we calculate the slope of this graph, we can calculate the average speed of each of these objects. So if I asked you for the blue car, and that's the blue line right there, what is the average speed of this object? Well, I can look at the outside points here. I know it starts at 0, 0, and I know it goes to 5 and 3, somewhere between 3 and 4. Let's look that up on the table here. So 5 and 3.4. So for the blue car, if I wanted to know its speed, v, I would just find the slope of this line using those 2 points, just like you did in Algebra 1. So it's going to be, for the velocity, it's going to be y2 minus y1 over x2 minus x1. All right, call this point 1, call this point 2, and we will have 5 meters minus 0 meters divided by, let's see, x2 is 3.4 seconds minus 0 seconds. And that is equal to, well, 5 minus 0 is just 5. It's in meters. Divided by 3.4 minus 0 is going to be 3.4 seconds. And 5 divided by 3.4 is equal to, let's call that 1.471. 1.471 meters per second. So on average, the blue car was traveling at 1.471 meters per second. And if you look at this, you can see that its slope stays pretty constant. It's pretty much a straight line. Yeah, okay, it's a little bit weird in this bottom section right here, but that's just when it's getting started. Once it gets started, it's pretty much going in a straight line the entire time. Now, what about this red one? What's going on with the red car? Well, you can see the slope is increasing as time goes on. That means, since slope is the speed, or the velocity, that means that this red car is going faster as time goes on. It starts off very slow, but it goes faster and faster and faster as it rolls down the driveway, which makes sense because that means it's accelerating. It has constant acceleration due to gravity down the ramp. Okay, so that's great. Could we calculate its average speed? Well, yes. This time, though, we'll take the outside points of the red one. Okay, yeah, that would, in theory, draw a line like this. And sometimes the slope of this is less. You can see down here at the beginning, sometimes the actual slope is less than the slope of the line that I drew. But at other times, the slope is greater, like up here at the end. The slope is greater than the line that I drew. So on average, we're going to be able to calculate the slope of this line in order to find its average velocity. So, okay, same sort of thing that we did. It's just out of Algebra 1. V is really the slope. That's y2 minus y1 over x2 minus x1. That's equal to, let's see, y2 is 5 meters. 5 meters. Minus y1 is 0 meters. Divided by x2 is 6.1 seconds. Minus x1 is 0 seconds. Well, that's going to be equal to 5 meters divided by 6.1 seconds is equal to, let's see here, 5 divided by 6.1 is 0.81. Actually, let's call it 820 meters per second. So we can find the average velocity by looking at these graphs and finding the slope. So, important thing to remember, number one, if you are graphing position or distance, or maybe even displacement versus time, if you're making that kind of graph, where position or distance or displacement, since they're all very closely related, is on the y-axis, and time is on the x-axis, for this kind of graph, the slope is speed or velocity. Depending on what you're graphing, if you're graphing displacement, you have velocity. If you're graphing distance, you have speed. Okay, so that's the first piece I wanted to show with you. But there's another thing I wanted you to notice about this graph. And yeah, I know it's kind of a mess right now, but take a look at it. This is basically a straight line. The straight line indicates that this blue car, the remote-controlled car, was moving at a constant speed, or a constant velocity. It was pretty much going at the same speed the entire time. This curve right here for the red car indicates acceleration. So if you see a curve on a distance time graph, or a displacement time graph, or a position time graph, slope is going to be your speed, and curves indicate acceleration. And you'll notice almost always the curves, if you look at this curve, let me clean this up a little bit and make it a little bit easier to look at. If you look at the original curve here, there we go. That's a little bit easier to look at. Okay, if you look at this original curve here, what kind of shape is that? Well, it looks like it's part of a parabola. And so curves that indicate acceleration are going to tend to be parabolas on this type of graph. So I have a couple video clips that I'd like to kind of sketch what sort of shape we would expect if we see an object moving and we make a position or distance versus time graph. So here's the first clip. Well, boy, wasn't that exciting. The ball went absolutely nowhere. Okay, so if you were to sketch a graph of what that looks like, what would we expect? Well, let's put in our axes here. We'd expect to have, if we are putting time over here and a position over here, we would expect to see that the ball's position stays the same. So that means it doesn't matter what time we have in the clip. I think it was about 5 seconds long. 1, 2, 3, 4, 5 seconds. Make that 5 seconds. It stays at the same position. If it starts right here, it continues at the same position. So this would be what we call a constant position object. And when you have a constant position, your position is not changing, which means you get a horizontal line on this kind of graph. Let's take a look at this second one. So in this video, the ball starts off at 0 and it rolls across the table pretty much at a constant speed. There's a meter stick there to kind of help us tell where it is at any given point, but I'm not going to make any measurements right now. I'm just going to sketch the general shape of this graph. So we should see something like this. It rolls at pretty much a constant speed. It starts at 0, and its distance from 0 increases. Suppose I should be a little bit more careful here. This is time. This is position. And our object is increasing its position as time goes on. It's moving along the meter stick, and the numbers are getting higher and higher and higher as it goes. Okay, take a look at this one. So in this video, the same thing is happening, except it's faster. You can see the ball is rolling faster. So what does that mean? Well, it starts off at 0 again, but its increase in position is faster. It goes to the same amount of distance in a shorter amount of time. So we would expect to see a greater slope here because it's traveling faster. By the way, things in this, along this type of graph, these objects are moving with constant velocity. Okay, take a look at the next clip. So in this video, the ball is rolling the other way. It starts off at 100 on the meter stick, actually past 100, and it rolls back towards 0, eventually passing it. So what kind of graph is this going to look like? Well, it should be a straight line, and because it's going the other way, it should have a negative slope. So it starts off at a fairly high position and goes back down towards 0. Maybe if I use a ruler, that'll come out better. Starts at a fairly high position, goes back down to 0, and does something like this. Again, it's moving at a constant velocity, and straight lines indicate constant velocity. The fact that it has a negative slope indicates that this ball is going the other way. Okay, one last video clip. So in this video, I put the ball on a ramp that is slightly inclined. One side's a little bit higher than the other. And so as the ball rolls down the ramp, it gets faster and faster and faster. In this video, we have what we call constant acceleration. And the phenomena that we see there is very similar to what we saw on that red car as it rolls down my driveway. It's the same sort of thing. So we can expect to see the same sort of graph that is formed. We could predict that we will have sort of half a parabola here as it gets faster and faster and faster as it starts to roll down the ramp. Now there's a lot more information that we'll get into more details in later lessons. For now, there's just two important things you need to remember. One of them is that the slope of this type of graph is velocity or speed. And second, we need to understand that acceleration shows up as a curve, most often a parabola if it's constant acceleration. So there's a lot more information out there on these graphs and different types of graphs, but I hope you've developed a basic understanding. Mahalo for watching, and see you next time.